Okay, everyone. So we are looking at section 6.3 today. The titrations will actually go through this section and the next. So this is just looking at the the acid-base titrations where we have not really any applications, but more from the calculation, like quantitative standpoint. So in order to have titration even be a possibility, you have to have only one reaction that will occur between the solutes, okay, in the two solutions. So you don't want to have things that will have multiple reactions or side reactions that are happening. Pardon me. The reaction between those solutes should be relatively rapid, right? So that way when you add your drops from your two solutions, that you're not waiting for that reaction to occur. It should be relatively quick. And of course, you have to have some way of signaling the point at which the reaction is then complete. So this is called the equivalence point or the stoichiometric point of the titration. So this is where essentially you have the number of moles, which is actually written right here, the number of moles of your hydronium being equal to the number of moles of your hydroxide. Okay, so meaning that they are equivalent. So when you're looking at the volume added, you're looking really how much had to be added in order to reach this equivalence point. Now, how we have this way of signaling is actually what an end point is, which we will get to. So that's where you add an indicator, which will then change colors at that point where you reach equivalence. So equivalence point is like mathematically where you have your equivalence moles reached. The end point is a visual cue or signal to acknowledge that. Okay, so here's a typical setup for titration. So you have, usually in an Erlenmeyer flask, you have the analyte, which is the one that we are trying to, usually it's determined an unknown about it. So maybe you're trying to find, maybe we don't know what the concentration is, or we're looking for something, maybe percent purity. We're looking for something about this analyte. So this is the thing that we are analyzing. That's where that term comes from. And of course, you have your indicator added there as well. So you can visually, with your eyes, when you're doing this titration, you can say, oh, okay, I know when to stop because I've reached the end point, which is signaling the equivalence point. Okay, so in your burette, this is where you have your standard solution. So this is the one that we have the known concentration values of. So in other words, it also goes by the term titrant. So this is what you are adding in drop by drop with the valve here, of course, on the burette in order to reach equivalence. So the one that is in the burette is what we know the concentration of. The analyte is something that we do not know, or we're missing a piece of information. That's what we're trying to solve for. Now, in order to prepare your analyte, usually you'll use a volumetric pipette in order to do that. So the solution that's being analyzed, let's say we want 10 milliliters of it. We would use a volumetric pipette because it is actually more accurate than reading it from a graduated cylinder. So it's just the most accurate reading that you can get for a volumetric pipette. Just like if you remember, I'm talking about different flasks, right? When we make the standard solution, we make that in a volumetric flask, right? So meaning it's very accurate in terms of volume measurements. Okay, so let's take a look at some practice problems here of determining some unknowns. Okay, so we have here a volume of NaOH. And if we require this much to neutralize, we have an acid here, we have the concentration, and we have the volume, right? So we have volume and concentration, we have volume of the NaOH. We want to know the concentration of our NaOH. So let's write out our reaction here quickly. So here we have a neutralization reaction that is happening. or double displacement, however you want to think about it. So C2O4 or oxalate. And to balance that out, we need a 2 and a 2. Okay, so let's write out the information that we have. So we know the volume of this, which I'm just going to convert this directly into liters. We know when we're going to be dealing with concentration, it's C is equal to N over V, and that has to be liters, right? So I'm just going to, right off the bat, we're going to do that. And this is what we're trying to solve the concentration of. Over here, we have the volume of our acid, 0.025 liters, and concentration is given. So this is essentially standard stoichiometry. So what we want to do is we want to solve for the moles of our acid, and we know that since it says it's being neutralized, that value of moles is going to be equivalent to the value of moles for our sodium hydroxide. Now we do have to consider the mole ratio, but we can get going to do this. So N is equal to C times V. So this is going to be 0.0521, or you can look at it as moles per liter, times 0.025 liters, right? So we end up with 1.3025 times 10 to the negative 3 moles. Okay, so this is moles of acid. So really if this was a 1-to-1 ratio, or if they were the same, 2 and 2, 1 and 1, whatever it is, then this number of moles would be equal to the number of moles of our NaOH. But because it is a 2-to-1 ratio of our H2C2O4, right? So remember, this is moles of H2C2O4, so that cancels. So essentially, this mole value is going to be double. So looking over here on this side, so this is going to be 2.605 times 10 to the negative 3 moles. Now that we know the moles, we would plug this into C is equal to N over V, right? So our concentration for NaOH is going to be our mole value divided by our 0.02156 liters. So the concentration we get here, and let's just confirm, so sig figs is going to be 3. So this should be 0.121 moles per liter. Okay, so you find your moles, you do the mole ratio, and then you can find your unknown. Okay, so this question is actually very, very similar. The only difference is instead of giving us, instead of solving for moles by doing C times V, we're given the mass value. So we have to do mass over the molar mass. So let's take a look at this one. So we have sodium carbonate, and that's reacting with a nitric acid, which is going to be sodium nitrate, and that's going to be carbonic acid at the end of the day there. Okay, and then this is going to be a 2 and a 2. Okay, so we have the volume is given for this nitric acid. So we have 0.02317 liters. So I'm just always going to be converting it into liters at the beginning. We want the concentration of this. Okay. Now, we're adding, there's a little bit of maybe an extra step added in here. So it's saying that we're taking this mass and dissolving it in 250 milliliters in a volumetric flask. So our concentration of our sodium carbonate is going to be our, oh boy, we have to do our 1.546 grams, and then we have our molar mass, which is 105.99 grams per mole. Oh my gosh, I'm writing grams per mole, but then I wrote moles there. Yeah, so grams. Okay, so grams cancel, and we want moles per liter, right? So then this is essentially going to be over 0.25 liters, right? So we're going to have moles per liter. So this value here is 0.0583 moles per liter. Okay, so this is the concentration before if you take a look, it says that they're taking a 25 ml aliquot of that. So this concentration, of course, is the original concentration, but that's not our mole. We don't use this yet. We got to find our number of moles. So the volume here is 25 mils. Oh my goodness, I said I was going to convert to liters and then I didn't. 0.025 liters. The concentration here is 0.0583, right? So it's just the added step with, instead of them giving us the concentration, we have to then solve for it. So our moles for our base, in other words, is going to be C times V, which should be this value, 0.08583 moles per liter times 0.025 liters. So that gives us our moles of our sodium carbonate, which is 1.458 times 10 to the negative 3. So that is for Na2CO3. And then our mole ratio, for every 1 Na2CO3, we have 2 nitric acids, right? So basically we're going to double this to get our mole value for our acid. So this is then, did I make an error here? No. So this is 2.915 times 10 to the negative 3 moles. And that is now for HNO3. So then to solve for the concentration, right, we have the volume and we have the moles. So we're just going to do N over V. So concentration for nitric acid is going to be our moles, which is this right here, divided by our volume, which is 0.02317 liters, which gives us an answer here of, let's see, sig figs, 4, everything's 4 actually, so we need 0.1258 moles per liter. Okay, so this first kind of set of calculations is just simple stoichiometry, probably from what you have done from grade 11. Obviously, it's been a little while, so it's nice to review that. So you find your moles of whatever you have all the information on. You then do the mole ratio, and then you solve for your unknown. Okay, so now we're going to be looking at, obviously, so that was kind of a little bit of a warm-up, and we're going to be looking at some example calculations or scenarios that you're going to come across. Okay, so obviously the first one we looked at is just finding the unknown concentration. So concentration we've done, we can look at that a little bit more in depth, but we can also be looking at, well, what is the volume that we're going to need? We can also determine, you can sometimes have an unknown solution, but you can determine the molar mass if you have the information from the titration reaction, and you're going to see an example of all of these. And we can also determine the percent purity. So just because you have a mass of an acid, so going back to this example, right? So this is saying that it's pure anhydrous sodium carbonate, but you may have a situation where the mass that's given to you is not pure, which means we can use titration to actually determine of that 1.546 grams, how much of this is pure sodium carbonate and how much of it is not that reactant at all, and maybe just a filler or an impurity. Okay, so we're going to go through all of these different titration calculations. All right, so before I start off with this next one, I'm just going to pause the video here for the next part.